Okay, AP Chem. This is going to serve as an answer key for the combustion analysis problems. So remember that when you combust something, it means to combine it with oxygen chemically. If you combust a hydrocarbon, means that you're going to form carbon dioxide and water, because carbon dioxide and water are both stable, happy compounds and will form if given the chance. So let's read the first problem. This is number 1. A hydrocarbon fuel with only carbon and hydrogen is fully combusted to yield 23.118 grams of carbon dioxide and 4.729 grams of water. Find the empirical formula. So the first thing we do, and remember there's more than one way to do these problems, but this is the way we learned. If you decide to do percent composition, you can do that also. So first thing I do is change grams of carbon dioxide to moles of carbon dioxide. And then I'm going to pull out that 1 mole of CO2 as 1 mole of carbon. So that's going to give me 0.52529 moles of carbon dioxide and moles of carbon. It also says I have 4.729 grams of water. I'm going to pull the H out of this one. So 18.016 grams of water in 1 mole of water. And then 1 mole of water has 2 moles of hydrogen. So remember, 1 mole of water molecules has 2 moles of hydrogen atoms. And that's going to give me 0.52498 moles of hydrogen. And you can divide these if you want, but you can see that to a very little extent, these are both very similar numbers. So our next step is to divide by the smallest number if you need to do that step. And you'll see that you basically get 1 to 1. So the empirical formula for this compound is CH. That's as far as we can go with the information that we have been given. Okay, let's do number 2. We're going to do it exactly the same way. So 38.196 grams of CO2. And I'm going to pull out the CO2, the carbon out of the CO2. First, we have to change it to moles. And that's going to give us 0.86789 moles of carbon. We'll do the same thing with water. And when it comes to hydrogen, I have 2.08171 moles of hydrogen. I had 1.048085 moles of water, but that each water has 2 moles of hydrogen atoms. Now we're going to do a division again. We're going to compare by dividing is the next step. So here we get a 1, and here we get a 2.40. So CH 2.40 doesn't make any sense because I can't have a part of an atom. So I'm going to have to find a number that I can multiply 2.40 by to get a whole number. Essentially, our problem is that 0.4. So if I multiply 0.4 by 1, I get 0.4. I multiply 0.4 by 2, and I get 0.8, not a whole number. By 3, I get 1.2, not a whole number. 4, I get 1.6, not a whole number. But if I multiply it by 5, I get 2.0. That's a whole number. So that's our target number here. So 2.40 by 5 is going to give me 12. And then I have to do the same thing to the 1, also have to multiply it by 5 to maintain that ratio. So carbon gets a 5, hydrogen gets a 12. So this is my empirical formula for number 2. Okay, here's number 3. We have 12.923 grams of CO2. Which gives us 0.29364 moles of carbon. 6.608 grams of water. Gives us 0.73357 moles of hydrogen. And then the nitrogen, let's look carefully at the nitrogen. So we have 2.501 grams of NH3. And 17.034 grams of ammonia. So we're going to do exactly the same thing that we did with the other ones. This time we're going to pull out the nitrogen. And that gives us 0.14682. Compare by dividing. And the empirical formula is C2H5N. Now, number 4 is a little bit different. So we have 12.915 grams of a biochemical substance containing only carbon, hydrogen, and oxygen, and it was burned in an atmosphere of excess oxygen. Subsequent analysis of the gaseous result yielded 18.942 grams of CO2 and 7.749 grams of water. From this, I get that I have 0.43040 moles of carbon. Now, this is one of the cases where we actually need grams of carbon. So you can keep going and get to grams of carbon, or you can just calculate afterwards by multiplying by the molar mass. and I get 5.1691 grams of carbon. And 0.73357 moles of hydrogen, which is 0.86024 moles of hydrogen multiplied by the molar mass, and that's 0.86712 grams of hydrogen. So now we know we have 12.915 grams, which is carbon, hydrogen, and oxygen. And we know what carbon is and we know what hydrogen is. So if we take this combination of carbon, hydrogen, and oxygen, subtract off carbon and subtract off hydrogen, we'll get the amount of oxygen, which is 6.87878 grams of oxygen. I divide by the molar mass of oxygen, which is 16, and I get 0.42992 moles of oxygen. So now I'm going to compare by dividing. And I'm going to get 1, 1, and 2. So my empirical formula in this case is CH2O. All right, here's number 5. 33.658 grams of oxygen was used to completely react with a sample of hydrocarbon in a combustion reaction. The reaction products were 33.057 grams of carbon dioxide and 10.816 grams of water. Determine the empirical formula. So this time we need to figure out how much oxygen was used. Now you know that oxygen is O2, but O2 is also all oxygen. So when you're changing, you can do this a lot of different ways, especially this one. You can do a lot of different ways. Like I could say, we could say this is O2, and then there's 32 grams of oxygen in 1 mole of oxygen, and 1 mole of O2 has 2 moles of oxygen atoms. You could do it that way, or you could just go straight to, I know that this O2 is all O, so 33.658 grams of it is O, and then you can go straight there if you like. So this is going to give me the fact that I have 2.1036 moles of oxygen atoms. So here's what I'm going to do with this. I'm going to figure out how many moles by stopping here. And then I'm going to continue on and get the grams by continuing on a little further. So this is going to be 9.0210 grams of carbon, or 0.75112 moles of carbon. And now let's do the same thing with oxygen. And I'm going to continue on to get grams of oxygen, of hydrogen. But I know that I also need the moles of hydrogen. So this gives me 1.2103 grams of hydrogen, or 1.2007 moles of hydrogen, like such. So now if I compare, this is a hydrocarbon, so if I compare by dividing 0.75112, 0.75112, here, of course, I get 1, but down here, I get 1.6. Now I have to figure out what can I multiply this by. And I can do the same thing as I did in the first one. If I multiply it by 1, it's 0.6. That's not a whole number. If I multiply it by 2, it's 1.2. That's not a whole number. If I multiply it by 3, that's 1.8, not a whole number, so on and so forth. So I'll know that I'll have to multiply it by 5. When I multiply 1.6 by 5, I get 8. When I multiply 1 by 5, I get 5. So my empirical formula is C5H8. There are more than one way to do these problems. And this is a good example of a problem where I could have done a couple different ways. Here's the last one, number 6. Number 6 may seem different, but it really isn't. So we have a compound that contains nitrogen and hydrogen, like such. And we did a combustion analysis on it, meaning we burned it with oxygen. Now, nitrogen is going to form its happy gas, which is NO2, and hydrogen is going to form its happy gas, which is H2O. So nothing really different about this. We're going to take the NO2, 9.82 grams, and we're going to pull out the nitrogen. To get 0.21343 moles of nitrogen. We're going to do the same thing for the water. And pull out the hydrogen. To give us 0.42740 moles of hydrogen. Nothing really any different. Now we're going to compare by dividing. And get 1 and 2. That means the empirical formula for this compound is NH2.